And we're going to start off with a story that's near and dear to my heart, which is about this interstellar visitor.
That's right.
So just to kind of set the table for context, because there's a certain Harvard physicist who has been used in a lot of the headlines around this story, Dr. Avi Loeb, who's the professor of astrophysics at Harvard. And funny enough, for those who might not know, I am the director of operations at a nonprofit called the UAP Disclosure Fund, where we are actively working with members of Congress and the executive branch to push for disclosure around these weird things that are flying around.
Mm-hmm.
And it just so happens that our favorite Harvard astrophysicist, Avi Loeb, is one of our advisory board members. So as soon as I saw the headlines of Harvard astrophysicist says, I knew it was Avi.
Yeah.
And I know...
And you've met him.
Yeah.
Yeah.
He's he's hilarious.
Yeah.
He's just so funny, witty, charismatic. It's not a surprise he's been as successful as he has.
Yeah.
Because in the industry, it's both. You have to do the work, but also be able to sell it.
Yep.
But I think what's been interesting is how this story has cascaded all over the place.
Yeah.
It started with an initial observation, and it seems like we've had some follow-up observations from, things like the Hubble Space Telescope.
Yeah.
So I'm really excited to kind of get your perspective on what exactly is going on here.
Yeah. So, I hate to break it to you, man, but it's probably not aliens. I tell you this
Not
every
today.
time. We've known each other for a while, and every time it's been
Every
like,
time. Not this time.
yeah, not this time. Not this time again. It's probably an interstellar comet.
Okay.
But it is still really, really, really cool.
Okay.
And I want to see more pictures. Okay?
Mm-hmm.
Putting it out there, could be other stuff, but it is very likely just an interstellar comet.
And so I think what's interesting about this whole concept of interstellar objects,
Yeah.
Coming into our, into a near Earth or into our solar system, it's a relatively rare, at least from our ability to track it.
Our ability to track
Track
it. That's the thing.
It is.
The first one was Oumuamua, I believe it was called.
Yes.
That was in the late 2010s.
Yes.
So just maybe probably less than 10 years ago.
Yes.
And then the next one that came out was 2I Borisov.
Yes.
And then this is the third one.
Both of which Avi was, one of the first early movers on really working on them. And so we don't really have a lot of context or data by which to sort of do analysis on this, which is why it's so important that we've had astronomers using Hubble to sort of point at it and say, hey, what data can we gather around this?
Yeah. This one is really nice because we caught it on its way in.
Right.
Okay?
Right.
Oumuamua, we caught it on its way out. Mm-hmm. So we can't get good data anyways. The data has really high error bars where we don't know if what we saw is like, if the number that we got is the true number, if it's plus or minus some big thing. Now we see it coming in. Mm-hmm. So it's really nice that we can chart its trajectory.
Yep.
And we can schedule observations.
Yep.
Okay.
Yep.
And that's, I think, going to be key to really understand what this thing is, because, this thing is most likely an interstellar object that is just going through the Milky Way at an incredible speed.
That's one of the things I think that's been pointed out in a lot of the news stories is that it's moving so quickly.
Yeah. It's moving extremely quickly.
And I guess one of the questions becomes, how do we do analysis on, or what are the characteristics that we would look for in an observation like this to distinguish it from just saying or what are the attributes that make you sort of make that conclusion to say this has attributes that are similar to comets or other sort of rocky objects that we've seen even locally?
No, that's a good question. To really get into that, let's talk about sort of the history of how we found this thing, right? Yeah. So we found this thing back when it was about 4 or 5 astronomical units away from the sun. An astronomical unit is the distance from the sun to the Earth. Okay. So it's 4 or 5 radii away from the Earth. Okay. That's when we first spotted it. It was out at near the orbit of Jupiter.
So we spotted it relatively close.
Relatively close, yeah. It's moving extremely fast, 58 kilometers per second. So that's one Earth orbit, one Earth orbit radius a month.
Okay.
which is like really fast, dude. Like it takes us years to get to Jupiter, and this thing is gonna be here in like 4 months.
And I want to be specific. When you say orbit, you mean orbit around the sun, not the rotation of
No,
the Earth.
yeah. This is the radius of our orbit around the sun. It's doing that in a month.
So what would take us 12?
Yeah, what would take us like years. Yeah.
Makes sense.
To get from here to Mars usually takes us a year.
Fair.
This thing is gonna do it in
true,
like,
because you're talking about traveling through space at a target.
yeah.
And so
and this thing is just coming at us like in a month. So this thing is incredibly fast.
Okay.
When it was really far away, and it was first spotted, we thought it was like 20 kilometers big.
Okay.
Which is massive.
Yeah.
Okay, that's like a big comet, big asteroid.
I think in the movie Deep Impact, the asteroid that was hitting Earth or whatever was like 1 to 3 kilometers. It was significantly smaller.
Yeah, significantly smaller, and that thing did damage. right. So this thing is like at least it's a life killer. It's a mass extinction type thing.
Yep.
If it came, especially at that speed, like
no chance.
We'd just be wrecked. So it's incredibly fast. And we thought it was incredibly big. Mm-hmm. The other thing that we thought was, it was really far away. We couldn't see any gas coming out of it, like what normal comets do when they come out from way out there. They usually have a buildup of ice, and then when they get closer to the sun, they should start having this tail, which is from all the ice,
famously known as the cometary tail.
Yeah.
Which was what was originally interesting about Oumuamua was, and the problem was we were catching it late, so we couldn't have enough data to tell. But the lack of a cometary tail was one of the reasons by which it was like, well, it doesn't look like the other rocks that we've seen flying through space.
Yeah. So this one, it was similar, right? And that's when Professor Loeb came out and was like, this could be something weird. We should take a closer look. It could be aliens. And a lot of astronomers at the time came out and said that, well, it's like too far away for us to really get good data. Okay. With astronomy, that's always the name of the game. Like, it's hard to get data on these things. Now I think it's been a month since then.
Yep.
A month or two probably since then. It's come closer. Now we see a tail.
Okay.
We do see a tail.
We do see a tail.
We see. We also see a sun-facing tail.
How do you mean?
Okay, so if there's the sun, the comet is moving like this. You'd expect there to be a tail that's going in the back, right? Because it's like leaving stuff. Going behind. There's also a tail facing towards the sun.
Got it.
And that is something that we know comets do.
Okay.
Because of something called sublimation. If you've ever seen dry ice, like dry ice just goes straight from solid to vapor carbon dioxide. Right. It doesn't go in. There's no liquid CO2, right? Because the air pressure is actually just too low to have that. So the phase changes go straight from solid to gas. Same thing is happening on this comet.
Okay.
Like the water ice is getting bombarded by the sun's rays, and then it's just boiling off. There's no so it's called sublimation, and that creates this like gaseous sort of water vapor halo around the comet. The Hubble Space Telescope made an observation of it not too long ago, and it updated the size of this thing. The size of this thing, we thought it was 20 kilometers. It's now something like 0.3 to 5 kilometers.
Okay.
Significantly smaller.
Yes.
And it is most likely smaller than 1 kilometer.
Okay.
Okay. Now, also what's interesting is the error bar is so massive. It's going from 0.3 kilometers to 5 kilometers,
that's pretty
right?
Wide range.
It's a pretty wide range. It's almost tenfold. In the variation. And that's just because like with comets, the nucleus is shrouded now. If you look at that photo, right?
Yes.
The nucleus is shrouded by this gas now.
Right.
So now it's really hard to resolve like what's happening on the very inside.
It's a force field, I promise.
Yeah, it's something like that. It could be.
But I think what's interesting here, I mean, this kind of goes to why the instruments we use for detection really matter, because it's what allows us to get sort of a high fidelity data set to then be able to do analysis. And also being able to do so repeatedly over time, such that we can continue to refine what that analysis is.
And as it gets closer and closer, we're going to be doing more and more. Because this is, at the end of the day, this is an incredibly interesting object, okay?
Right.
If we were to run back the clock on where this object came from, this 3-eye atlas, okay, it's an interstellar object. And if we were to run back the clock on where it came from, it would come from the depths of the Milky Way. And especially in this region of the Milky Way that's like right above our disk.
Okay.
Okay, it's called like the thick disk. Okay, so the Milky Way is like this, right? You've seen the Milky Way across the sky.
Yes.
Most of that stuff is in the thin disk. Okay, that's where the like stars and the gas sort of is. So when you look up at the night sky in a national park or in a really dark area, you'll see it going across the night sky. That's usually just the thin disk. Right above that thin disk is something called the thick disk. Okay, and this has an old population of stars.
Okay.
Really old.
Okay.
Like older than our solar system. And if this object came from up there and it's like sort of, you know, crossing down into our neighborhood, then it came from those objects, which means that, you know, we're estimating this thing to be 7 billion years old.
Wow. Okay.
Which is older than our solar system.
Right.
So this is actually the oldest object that we've seen in our solar system.
Which is
it's older than everything else.
That's around. It's basically like it's, you know, a quarter of the age of about half the age
of the universe. Yeah.
Which is fascinating.
Yeah.
I mean,
we're about a third, right?
Right.
But like, yeah, this thing's like half.
Look, I'm not saying it's aliens, but they've had time.
They have had time, and they might live up there, you know. So, but we definitely know that it's old. Like, if it's a naturally occurring rock and it came from up there, it's probably really old.
Very old.
Right.
Fascinating.
The other thing that's kind of crazy is like how fast it's going. So how do we explain that?
Right.
Well, that can be explained by just close encounters of the gravitational kind.
Right.
Okay.
So it was passing through, you know, from the thick disk through the thin disk, and at some point it passed a very, very massive object.
Yeah, it passed a very massive object in exactly the right. I mean, this thing's been around for 7 billion years, right? So, and if it's like out here, who knows how long it's been roaming the cosmos?
Right.
Right. So, you know, in the 3-body problem, if you remember, right, like tiny little deflections can cause something to just shoot out, right? Yes. You can imagine the same thing here. Like spacecraft, NASA uses these things called gravity assists to boost the speed of spacecraft all the time. This thing could have had a very close encounter with a massive object, let's say another star, and it was just like shot out.
And then ended up being shot out in our direction.
Now, the direction that it was shot out in is very peculiar. Right?
Okay.
Because the sun and the planets form an ecliptic plane.
Yep.
Where we all sort of like, this is the primordial angular momentum of the solar system coming to fruition as like one plate where all the planets reside. And this thing is coming in at like a really shallow angle, right? Of all the angles that it could have chosen, it did choose this weird shallow angle.
Okay.
That's a little weird.
Okay.
I'll
take it.
Oumuamua did not do that.
Okay.
Right? So you know, you could say, well, you didn't use it for that one, and then now you're using, you know, so like it again, it could just be coincidence. This is the first 3 that we've done, and this is one that like it's as people are saying, it's like taking a tour of the solar system, right? It's going through Jupiter, it's going to visit Jupiter, it's going to see Mars and Venus. It's not going to see Earth. We're actually going to be on the other side of the sun.
Got it.
So it's going to, like, if the sun is here and we're here, it's going to like move over there.
It'll pass through generally where our orbit would be. We're just in the wrong place.
Yeah, we're in just in the wrong place at that time. But then it's going to go see Jupiter later. And actually, there's a proposal out in Astrophysical Letters, I think by Professor Avi Loeb, that wants to get the Juno spacecraft, which is around Jupiter.
Yes.
They just want to like boost it a little.
Yes.
And they calculated how to do it. You boost it a little, you get it into a higher orbit around Jupiter, and then it'll make a really close encounter. And it'll make a real close encounter. I think that would be really cool, actually. Personally, I think that would be a great use of Juno.
It seems like, and this is a call to those who may be watching that are in the annals at NASA making decisions. Given we don't have a lot of historical data about interstellar objects passing through our solar system, it seems like, and the fact that there are always chance opportunities.
Yeah.
This seems like an incredible opportunity with relatively low lift.
Yeah.
We've done the math.
Yeah.
It can be done. Do we want to waste the fuel? Hey, look, when's the next time we're going to get a chance to capture an interstellar object at that proximity?
Yeah.
Especially given where our orbit is. That means like on Earth observatories.
Yeah, we're not going to be able to, because we can't like point at the sun.
Right.
It's going to be behind the sun. So like, what are we going to do? Already though, like so many people have like imaged it. Hubble Space Telescope imaged it. The Very Large Telescope, the VLT that we talked about in one of the previous episodes, that imaged it. Gemini North, another telescope that we've talked about in previous episodes, that imaged it in Hawaii. So we've had like tons of interest in this thing because it's obviously interesting. It's a 7 billion year old object that's coming to visit us. right. That's like, it's incredible.
We have to have the doorman to check to make sure security is tight. You know, hey, who are you and what intentions do you have with our daughters?
Yeah.
And it appears that it's going to be making its closest sort of approach to us in the late October, early November 2025 time frame, which is why everyone's freaking out that there's an alien invasion in November.
I mean, if we find out it's aliens, then the stock market crashes. I don't know what happens to Bitcoin. You know,
but we will find out soon. It's not too long away.
It's not too long away. And actually, you know what's hilarious? 6th of August. What's today's date? The 12th?
Yeah.
So 6 days ago, the James Webb Telescope imaged it.
Oh, interesting.
But they haven't released the data because there's a 3-month embargo on whoever gets the time. Like, so whoever like had that time was like, I'm going to put it here, and then like imaged it. And I'm sure that if like, that's another thing that gives me like some security is like, I'm sure if that dude like saw something weird, it would have NASA would have been like, nah, okay, we would have like someone would have said something by now. So it's been 6 days. It's probably something extremely interesting, and this guy's scrambling to get his paper out before the public gets the data.
That's
but it was like 6 days ago, and it's also going to image it again in December. So it's actually scheduled in December to do it.
Perfect. So
because that's when the Earth is going to be at exactly the right spot to like see it again, because James Webb is also, it's still tied to Earth. It's not like just out there. So
it's out there, but
so it's like now, and then we're gonna have like a few months where we can't. Because we'd have to point it towards the sun.
Which is why Juno is so important.
Yeah.
NASA, send Juno out there. Let's take some pictures.
Yeah.
We want to see it. It does look really beautiful and brilliant in the imagery we do have from Hubble.
Yeah.
And
you can see it's clearly moving, right?
Right.
Because like the streaks that you see there,
yes,
those are stars,
right,
that are not moving.
Right.
So the telescope had to like track it.
Yes.
And then as it was tracking it, the stars were like making streaks.
A nice space long exposure.
Yeah.
So while it may not be aliens yet, it will give us more data to, it's sort of like that in the sort of AI analogy, it's like that training data set of what we know as sort of prosaic data. And such, it gives us a better way to then tune for future potential visitors, if they're not already here.
Yeah, and it's going to be really interesting to see, like, once it gets closer and we take more data, it'll be really cool to see what this object is made of. Right? Because, like, we know what solar system comets are made of, but, like, are these older solar systems somehow different? Mm-hmm. Do they have different characteristics? We've already found water on it, mm-hmm. which is very characteristic of a comet. Mm-hmm. So, you know, in that respect, it's very similar. And we're expecting to find CO2 mm-hmm. and carbon monoxide. But it'll be interesting to see what else comes out, right? Like maybe there's like some other exotic chemical that we didn't even think a comet would have.
This actually ties to the story we previously covered about the importance of discovering the first molecule in the universe and how that then has this sort of butterfly effect in terms of how everything forms downstream. And this would be great insight to understand those earlier solar systems. And what's kind of going on there. Mm-hmm. This also makes me think we should do another episode on the idea of panspermia, where it's the idea that life is seeded from these comets that are traveling interstellar and carrying things like water.
Yeah. Like that would be that. I mean, this thing is carrying water, right? What else has it got? It'd be so interesting to see. And like, you know, the other thing I want to say is we've only seen 3, mm-hmm. right? And the reason we've only seen 3 is probably our inability to see the rest.
Fair.
Right? This might be super common. Right. We've only had like a giant network of telescopes doing this kind of stuff for not very long. Right. So it's not like, you know, all of a sudden someone turned on the Interstellar button
and
like
now,
in 2015 and now we're just starting to see stuff.
Right.
And for that we need like telescopes that are dedicated to just like finding this kind of stuff.
Which means we need to fund science.
Yes. Yes.
This is
and for that, we actually have a telescope now.